Stokes theorem for this function where S is the upper half of this sphere, the unit sphere, and C is its boundary. C is its boundary means if I am having this sphere, then taking this to be the boundary C, which is intersecting the xy plane. So this is the boundary C, which is in the form of the circle that is intersecting the xy plane. Because this is intersecting the xy plane, so here z is 0. So if I put z equal to 0 in this equation, I will be getting x² plus y² to be equal to 1. That is the equation of this circle. It's like if I cut this sphere into two parts, I will be getting the shape of the circle as the boundary of the sphere. So this is the circle C I am getting, which is intersecting this xy plane where z is 0. I hope it's very clear now. Okay, let's write this. So C is the unit circle which we are getting by putting z equal to 0 in the equation of this sphere. So this is for z equal to 0, the equation of the circle. Because we need to verify the Stokes theorem, so I am writing here, by Stokes theorem, the line integral of dot product of f vector with dr vector over C is equal to the surface integral of curl of f vector, its dot product with n vector ds, where the mod of n vector is equal to 1. What is n vector? It is the unit outward drawn normal to the surface S, right? Its mod is 1. So let's first evaluate the left hand side and get the answer, and then we evaluate the right hand side and get the answer, and then check whether these two answer matches or not. If they are equal, then the Stokes theorem is verified, right? Okay. So finding first dot product of f vector with dr vector. For I'm having this given f vector. So writing here f vector. So this is 2x minus y, I vector minus yz²j vector minus y²zk vector, taking its dot product with dr vector. So dr vector is dxi vector plus dyj vector plus dzk vector. This is the same example as that of the previous content. Only f vector is different. When taking the dot product, we get 2x minus y dx minus yz² dy minus y²z dz. Now taking the line integral of this dot product. So this is a line integral over C. Writing the value for this dot product. So this is 2x minus y dx minus yz² dy minus y²z dz. Because on this circle, z is equal to 0. So dz is also 0. Writing the first term as it is, second term becomes 0 and third term also becomes 0. Now I am going to use the polar coordinates to evaluate this integral, for which I put x equal to cos of phi and y is equal to sine of phi. R is 1. So putting x equal to cos of phi and y equal to sine of phi, so the line integral over C of 2x minus y dx, this is equal to the line integral 2x, that is 2 cos of phi minus sine of phi. From here dx becomes minus sine of phi d phi. And what are the limits of phi? It is from 0 to 2 pi. C is your circle, so the limits are from 0 to 2 pi. Multiplying minus sine phi with 2 cos phi. So this is 2 cos phi sine phi with negative sign plus This is sine square phi and then d phi. Now 2 sine A cos A is sine of 2A. So I'm writing this as sine of 2 phi. Using the identity 2 sine A cos A is equal to sine of 2A. The integration of negative sign outside, sine of 2 phi d phi plus the integration for sine square phi d phi, the limits from 0 to 2 pi. Solving the first integral, integration of sine of 2 phi is negative of cos 2 phi divided by 2. So managing this negative sign, we are getting cos of 2 phi divided by 2 with limits from 0 to 2 pi. Right? And I can write this integral as 4 times the integration from 0 to pi by 2 sine square phi d phi. Yes. So now putting the upper limit over here, I get cos of 4 pi, that is equal to 1. So this is 1 divided by 2 minus, when putting the lower limit, we are getting the answer cos of 0 is cos of 0, that is also equal to 1. So this becomes 1 by 2. So this is 1 by 2 minus 1 by 2, which is 0. So when putting the upper limit, we get 1 by 2 minus when putting the lower limit, we get 1 by 2, right? Plus 4 times the integration from 0 to pi by 2 sine square phi d phi. So first integral is 0 plus 4 times. Because I'm having the limits from 0 to pi by 2, I can use the reduction formula over here. For that, what is the power for the sine? It is 2. It is even power. We always subtract odd numbers from the power in the numerator till we get 1. So this is 2 minus 1, that's it. Divided by writing the power first and then subtracting the even numbers from the power for the denominator. So 2 minus even number is 2, so this is 0. So already we are getting 0, so we don't need to subtract any number from the power. And whenever we are having this even power, we always multiply this by pi by 2. So this is equal to, this cancelled out with this, so this is 2 and this is 1 and this is pi by 2. So that is equal to, this cancelled out and we are getting pi. So I'm having the value of this left hand side of the Stokes theorem to be equal to pi. Now evaluating this right hand side. For that, I need to calculate first the dot product of these two and then taking the surface integral. Okay, first let's evaluate the curl of f vector. What is the first component of f vector? It is 2x minus y. Then the second component is minus yz square and the third component is minus y square z. So this is I vector. Okay. Partial derivative of this with respect to y, it is minus of 2yz. Partial derivative of this with respect to z with minus sign, it is minus 2yz. Right? Minus j vector. Partial derivative of this with respect to x is 0 minus partial derivative of this with respect to z is also 0 plus k vector. Partial derivative of this with respect to x is 0 minus partial derivative of this with respect to y is negative 1. So this is I vector into, so minus 2yz plus 2yz, that is 0 minus this is 0 plus this is k, the k vector. So we are getting the answer to be k vector only. And now I am going to use the spherical polar coordinates to get n vector, and as mod of n vector is equal to 1, we write n vector to be equal to xi vector plus yj vector plus zk vector. Right? So for spherical polar coordinates, we put x equal to, yes, r sine of theta cos phi. Right? Because radius is 1, so I am writing this as sine theta cos phi. So this is sine theta cos phi I vector. Similarly, writing y to be as r sine theta sine phi, r is 1. So this is sine of theta sine phi j vector plus z is r cos theta, r is 1. So I am writing here cos of theta k vector. Is it okay? Fine? Okay. Now taking the dot product of curl of f vector with n vector. The dot product of k with k is 1. So writing here cos of theta. That's it. Okay. Now taking the surface integral for the dot product of these two. So this is the surface integral. Okay, what is their value? It is cos of theta. Right? Because I need to change this to the spherical polar coordinates. So ds becomes sine theta d theta d phi. So writing here sine theta d theta d phi over the surface S. So this is equal to, because I need to integrate this first with respect to phi, so I am interchanging these two. So writing here d phi d theta. What are the limits for phi? It is from 0 to 2 pi. And the limits of theta is from 0 to pi by 2. Right? So now integrating this with respect to phi, we are getting phi into cos of theta sine of theta with limits from 0 to 2 pi, and here writing d theta. Putting the upper limit, we get 2 pi into cos of theta sine theta minus, when putting the lower limit, we get this to be 0. D theta. Taking this 2 pi outside of this integral, and writing here cos of theta sine theta d theta. Substituting sine of theta to be equal to t. So this is cos of theta d theta equal to dt. So this is 2 pi. Okay. Writing the limits for t. When theta is 0, then sine of 0 is 0. So the limit of t is 0. When theta is pi by 2, sine of pi by 2 is 1. So the limit for t becomes 1, the upper limit. And writing sine theta to be t, and cos theta d theta becomes dt. So this is equal to 2 pi. Integration of t is t square divided by 2 with limits 0 to 1. Cancelling this 2, and we are getting this to be pi. Okay, putting the upper limit, we get 1 square, that is 1. Minus putting the lower limit, we get this to be 0. So we are getting the answer for the surface integral to be pi. The same answer, right? So the value for the right hand side of this integral is also equal to pi. That means Stokes' theorem is verified. The line integral of f vector dot product with dr vector is equal to pi, and this value is also equal to this surface integral. So we say that from here, therefore, Stokes' theorem is satisfied. Okay, thank you.